Hello students, welcome to Young Cubs. Today is the last session of this chapter, Forces and Energy. Okay, today we are going to start with the ways heat gets transferred to the surroundings or to the object next to it. Okay, so in the previous chapter we had spoken a lot about heat and thermal energy. We also looked at the difference between the terms heat and temperature. Okay, we always spoke about temperature, what it does or what does temperature tell us. Okay, and the first thing was the direction in which the temperature or the thermal energy moves. Yes, but and then the heat gets transferred from one particle to the other, energizing it, making it more active, okay, reducing the intermolecular spaces and whatnot. But how does the heat get transferred? Children, there are three ways in which heat gets transferred. One is conduction, the other is convection, and the third is radiation. Yes, children, after reading this introduction page, okay, we shall talk about these three ways of transferring of thermal energy in detail. Okay, and how do we observe it in nature? How have the industries started using it in day-to-day life and processes? We'll get into the details. Okay, let's start. Heat and particle movement. When any substance is heated, the particle in the substance start to move faster. If it's solids, they vibrate. If it's liquid, they move around quickly. They start boiling. Okay, and as the bonds break. Okay, and in gases, what happens is the air, they move further apart, and the air basically, or the gas becomes less dense, moving upward. Okay, as they become light, as they become far apart, as they go far apart, they become less dense, and they rise above the air. Okay, above the atmospheric air, which is most dense at sea level. Yes, so in solids the particles move by vibrating around their fixed position. This vibration gets faster when the solid is heated. As the particles vibrate more vigorously, they take more space. Vigorously means with more energy, more speed, and more force. That means solids expand when heated. Okay, and expands means to increase in size or take up more space. In liquid, what happens when thermal energy gets into them? Okay, the particles also vibrate, but the particles are not in fixed position. Okay, when the liquid is heated, the particles vibrate faster and move around faster. Again, as the thermal energy increases, the particles take up more spaces. That means liquids also expand when heated. In gases, the particles are far apart already and move in straight lines until they collide with. So particles move in straight lines until they collide with another particle or the walls of the container. Now, when the gas is heated, the particles move faster and collide more with more force. Okay, and they collide more frequently also because they're moving fast. The speed is increased. The particles will take up more spaces in a gas and in a heated gas, so gases also expand when heated. So if a gas is closed in a container and there are gas particles in it, okay, because of the collisions. Okay, because of the collisions, they will more frequently bang to the walls, hence, they would require more space as they would expand. Okay, children, hope this much is understood. So, as I spoke to you, as I already had mentioned the names of the three ways the any substance transfers heat, okay, out of which conduction is the first one. Conduction is nothing but transferring heat by actually coming in contact with each other. By touching, the heat gets transferred. Okay, let's read. When particles are vibrating, they will push against the particles beside them. So, when, for example, this is vibrating, so it will kind of, when it moves, when it vibrates, it will have, it will push the particle next to it. The faster and more vigorous the vibration of the particles, the greater the push. Yes, this will cause the particles beside them also to vibrate. So if this particle is vibrating, okay, and there is a particle touching it, is in direct contact with it, this will also start moving. Then if the particle, another particle, this will also start moving. Correct? So that the movement or the vibration eventually shakes the other particle sitting next to it. Yes, this is how thermal energy is transferred by conduction, by coming in contact, by touching each other. Conduction of thermal energy works best in solids, okay, where the particles are close together and can only move by vibrating. Yes, if there is one solid particle, okay, and see, you put in when you when you in kitchen, basically you have a pan, a frying pan, okay, you put a roti or a slice of bread on it, okay, if you hold it just above, okay, if I say, if this is my frying pan, okay, there's fire below it, there's a gas, okay, if I keep the bread slice over here in the air holding it, will it heat up? No, it will not. I will have to place this bread piece on the frying pan so that when the pan, when this frying pan heats up, the heat, the bread that is in contact with it only then will get heated up. So what happens is the bread layer is touching the pan. Okay, due to the touch, the particles of the pan which get heated then transfer the heat to the part of bread or the particle of bread which is in direct contact or touching it. Yes, children, so the heat is getting transferred from the pan to the slice of bread with by which process, which way of transfer? Through conduction. This diagram shows how thermal energy is transferred by conduction through a solid. Okay, so by coming in direct contact. ठीक है? Metals are the best conductors of heat. So if there's anything, any metal, okay, it heats up really fast and it really quickly, it transfers the heat to another object in contact or in touch with it. Okay, because of the way of particles are arranged. So why are metals best conductors of heat? Because of the way the particles are arranged in them. The electrons that are free to move in a metal helps to pass all the vibration. So, taking any metal, we know that in a metal there are free electrons. If you've done property of metals and you've understood the electronic configuration of sodium or a potassium, they may have one electron in the outer shell or two electrons in the outer shell. The metals just want to get rid of these electrons because they are occupying one whole large shell. So they are happy to leave the electrons. So from these electrons, easily when they really get heated up, okay, they become active, they leave the shell and move out, carrying the thermal energy with them. Yes, wood, plastics, and fabrics such as wool and cotton are poor conductors, so they are not very willing. Non-metals also are not willing to transfer it. They will get heated up. Okay, they will absorb the electron, but then giving it out and transferring it to another atom or particle beside it becomes a little difficult. Okay, so they are poor conductors. Just as with electricity, the opposite of a conductor is an insulator. We say that poor conductors of thermal energy are good thermal insulators. They don't let the heat go out of them. Okay, some objects are made from materials that are chosen because of their ability to conduct thermal energy. Okay, so if I want to make a frying pan, okay, I'll choose a metal because I want my food on it, kept on whatever food that I keep on it, to heat up fast and get cooked up fast, rather than me having a wok or a pan made up of wood. Yes, it will not easily, it will get heated up, but it will not easily transfer the heat to the substance that it is touching or that is in contact with it. Okay, hope you've understood conduction. Look at the pan in the picture. The pan is made from metal because metal is a good conductor of thermal energy that helps the food to heat faster. The handle is made up from plastic because plastic is a good thermal insulator. So why is this handle made up of plastic, children? Do you want your hand to get scorched or burnt? No, right? So you don't want this high heat, getting transferred to the plastic and then your hand getting burnt. Yes, plastic does not transfer heat easily. Hence, these handles are made up of good thermal insulators such as plastic, wood, okay, that makes the handle comfortable to touch. The spoon is made from wood. Look at the spoon out here. This is also made of wood, which is a good insulator or a poor conductor of thermal energy. Clothes for cold weather are made from materials that are good insulators, that slows the conduction, that slows the transfer of thermal energy when they come or when they touch us. Okay? Conduction does not work well in liquids. Remember, children, this is important. Conduction does not work well in liquids because the particles move around more when heated rather than just vibrating. So they move around faster. They are not conducting, they are not transferring the heat by when they come in contact. The moment you touch it, maybe the liquid is moving around. Conduction also does not work well in gases because particles are far apart and the collisions are not very frequent. Conduction cannot happen in a vacuum because there are no particles important to vibrate in a vacuum. So, children, these statements are very important. When you get an application based questions, these are the ones that need to be straight away put into the answer to gain your marks. Now, what is convection? Convection, if conduction is direct touching, convection is not a direct touching. Okay, it heats up the space around it. Let's find out. When liquids and gases are heated, the particles move faster and take up more space. Taking up more space means the volume increases. Yes, the space around, the space around which it is spread out, or it is dispersed. Okay, that space has to be increased, the volume increases, the number of particle does not change, so the mass of the liquid or gas does not change. Do the particles from 10 particles become 20 particles? No, it's just that they move far apart from each other. For this equation, you can see that when volume increases and mass stays the same, the density will decrease. When volume increases, density decreases. We've done in our first two lectures that density is inversely proportionate to the volume. You will also remember that less dense substances float more than dense substances. Yes, we know that. So, if the air particles are close to each other, children, the moment they get heated up, they move, they become lighter, and not lighter, but they move away and they want to fly higher. Okay, and the heavier particles which are close and compact to each other, they come down. Yes, so what happens on a hot summer day? If this is a road made up of concrete, okay, now due to the sunlight, okay, due to the sunlight, okay, this road or the street has heated up. Okay, the air particles that are just above the street, okay, they also heat up. Okay, when they heat up, they want to drift away, they want to fly away, or they want to move apart from each other. But here, maybe the particles, this is the layer which is right above the street, but then there is another air layer which is above that, that is comparatively cooler because it is getting heat only from the sun rays and not coming out from the dark colored street. So they are comparatively cooler, so they come down and occupy the space from which the particles that were earlier there have moved up, so they occupy that space and come lower, and then again they also get heated up, they move higher. So convection, all in all, move the particles move in a cycle. The colder ones move down, the hotter ones go up, emptying the lower space, and that's how they move in circles. Okay, children, hope this much is clear. Let's read a little more. So, the same thing that I explained. So, the air, okay, here cooler air moves to take the place of the air that is rising. So, if take this as a typical scenario in which you have a microwave oven. Okay, what happens? Okay, this assume that this is a microwave oven. So here these panels out here are this panel out here is giving out heat. Okay, so this area is basically, or not that area, I can say that the bottom, this part of the oven gets heated up. The air just touching this portion. Okay, this is the floor. Let me put the floor in black. Okay, this is the floor of the oven. Okay, yes, the floor of the oven. So now the air particles which are directly touching, okay, the floor, okay, gets heated up. And when they get heated up, they want to move far apart and they apparently move upward. Yes, they move upward. Thus, warm air rises as it becomes less dense. Okay, now as it has risen on top, this warm air, okay, is comparatively less hot than the air which has come down. So cooler air is more dense. This falls down and comes in direct contact again with the floor. This again gets heated up, moves upward. Upward, it up or up on top is not so hot. That means it is cooler than the bottom layer. Hence, this is how convection moves in a circular format. Okay, hope this much is clear, children. Hope you understand that the space, okay, the space gets warmer. Okay, the space is heated up. The objects do not have to come in direct contact with each other. They don't have to touch each other to during the process of convection. When the objects touch each other, are in contact with each other and transfer their heat to the next one, it is conduction. But okay, due to heat, if something has risen into the air or has moved away from the hotter zone, okay, and then the space that becomes empty because the hotter particles have moved up, the lower particle, the cooler particles, since they are dense, they settle and move downwards. Then comes radiation. Okay, in radiation, as the name suggests, there are radiations which heat up a particular thing. So, like the sun radiations. Okay, there's the sun. Okay, sunlight and the sun's heat travels through a vast distance. So sun travels all the way, moves, comes down, passes Mercury, Venus, and then comes to Earth. So when it passes through Mercury and Venus in space is all nothing but a vacuum. There are no particles in space. Okay, particles come when where are the particles? The atmospheric particles or the air particles come, we find them only around Earth. Otherwise, so if this is the atmospheric layer which has air particles, okay, but here this area is only vacuum. It's the sun's heat radiations that can pass through the vacuum and enter our atmosphere. So through radiation also heat can be transferred. There is a vacuum in space between the sun and the earth. So conduction or convection would not transfer heat, the thermal energy from the sun to the earth. That means thermal energy must be transferred in a different way, children. Correct or no? Okay, this different way is called radiation. Radiation is a type of wave that we cannot see. Mobile radiations and various material. When you are treating cancer patients, that's when radiations are being given. So radiations are something that we cannot see. Thermal energy can be transferred by radiation very quickly. Yes, it barely takes time for the sun's rays, just around 8 minutes or so, to cover such a lot of distance to the earth. The thermal energy from the sun only takes about 9 minutes. Okay, it's 9 minutes, not 8 minutes, to reach earth. All objects give out thermal energy through radiation. Did you know, children, even our body gives out some kind of infra radiations, and due to which mosquitoes, get attracted towards us. The hotter the object, the more radiation it will emit. So our body is comparative is hot. It's on a warmer side. So our body also gives out these radiations. That's how mosquitoes come to know that, oh, there's heat coming from this direction. That means there's a human sitting there. Let me go and bite it. So emit means to give out. The sun and other hot objects emit thermal radiations by the thermal energy by radiations. Cooler objects absorb thermal energy by radiations from hotter ones. Okay, cool objects absorb thermal energy by radiation. Children, okay, now radiation can pass through a vacuum because radiation does not need particles. Radiation can also pass through transparent solids, liquids, and gases. Yes, we get the sun's heat inside, even though our windows are closed, because our windows normally are transparent. Okay, the best emitters and absorbers of radiation are dull and black substances. Shiny and white, okay, they reflect. They are the worst absorbers and emitters, and they are the best reflectors. Yes, children. So dull and black thing absorb and emit also. Okay, they give out. Okay, but okay, and then and when these substances are there in a large, spread out over a large surface area, more radiation. And if there is a smaller surface area, okay, obviously everything radiates, children. Everything gives out radiation, even the shiny objects, even white or silver objects, but it's very very less compared to dull and dark objects. Shiny white or silver surfaces reflect radiations away. Okay, they don't become hot easily. So that's the differentiation table between conduction, convection, and radiation. Let's quickly run through it. In conduction, heat transfer occupies between objects by direct contact. In convection, the heat transfer takes place within fluids. Okay, it heats up the space around. Okay, in radiation, heat transfer occurs through electromagnetic waves without involving particles. The heat transfer takes place due to difference in temperature. One solid particle will be colder than the other, so it gives out, or it touches, and the temperature changes. Heat transfer occurs due to difference in density. Children, very important. The dense particles settle down, the less dense particles rise up. The heat transfer occurs in all objects with temperature greater than 0 Kelvin. In conduction, heat transfer In heat transfer in conduction is slow. In convection, the heat transfer is fast, and in radiation, the heat transfer is the fastest. Heat transfer occurs through a heated solid object. Heat transfers occurs in through intermediate objects. Objects lying in the middle. Particles which are colder, which lie in the middle. Okay, remember the example of the street. The street is hotter, the air above it is cool, and the air above the cool layer of air is again hotter. So it's in the intermediate objects transfer the heat. Okay, heat transfer. So for example, heat transfer between air and water. Okay, heat transfer occurs through electromagnetic waves. It does not follow the law of reflection or refraction. Here, since there is the particles are around where, okay, the rays deflect, okay, they don't move in a straight line. So, okay, it does not follow the law of, even this does not follow the law of reflection or refraction. However, in radiation, okay, there are rays. If rays are involved, reflection and refraction will take place. Here rays are not involved. So refraction and reflection won't occur in conduction and convection. Conduction, convection and reflection. Most objects gain or lose thermal energy through these three ways in a combination. Not only conduction, not only convection, and not only it's a combination. Let's look at it. Okay, now there's a room heater in the picture which has hot water flowing through inside it. The thermal energy from the hot water is transferred to the metal of the heater. Okay, so it's by conduction. The liquid water particles are touching the metal particles, so it's by conduction. Thermal energy from the metal is transferred into the air, also by conduction. So whenever the air particles come in contact with the metal layer, they are coming in contact. So even that is happening through conduction. When the warm air expands, okay, it spreads out, it rises, which heats up the air above it by convection. Now, there apparently then again becomes an intermediate layer. A layer of cool air comes in contact again with the metal layer. The metal surface of the heater also emits, okay, radiation. Everything gives out radiation once it becomes warm. Okay, children, so it's a combination. Some objects are designed to reduce the effect of conduction, convection, and radiation. And the best example is your flask, a thermos, okay, what we call. Okay, let's understand this. This is quite important, children. Okay, vacuum flasks are containers used to store hot liquids such as tea, coffee, or soup. The flask is designed to slow the transfer. So, if there is hot coffee inside here, if this flask inside is filled up with hot coffee or hot water, okay, they don't want the heat to get transferred easily and this liquid to cool down easily. So it is designed to slow down the transfer of thermal energy by reducing the conduction and radiation. Okay, so inside a vacuum flask there is a glass bottle. So this, where are we? Okay, one second. So this inside is a glass bottle. Okay, so if there is, this is a glass bottle with a silver coating. There's a silver coating on the glass. Yes. The glass bottle is surrounded by a vacuum. So this space out here is nothing but a vacuum. Okay, and the bottle only makes contact with the outside of the glass at the top. So here only the lid is in direct contact with the glass. Correct? Okay, as shown in the diagram, the silver surface of the bottle reflects. So silver and white, as we studied on the previous page. Okay, here. Okay, shiny silver and white are the worst emitters and absorbers of radiation. So it is not going to allow so much of heat to get transferred. Okay, because silver surface is a bad, is the worst reflector or the worst emitter of radiations. Okay, so the silver surface of the bottle reflects thermal energy in the form of radiation back into the hot drink. So if this is hot, it's getting to this is in turn putting it back. Okay, it reflects the heat back into the liquid. Okay, the form of radiation is back into the vacuum surrounding the bottle prevents conduction. So this area is vacuum, so no substance is in that. So the particles, the substances out here may be in contact with the silver, with the glass. Okay, but the glass, however, is not touching the outer layer. There is a vacuum, as there's a vacuum space created between the inner glass vessel and the outer case. Yes, children. Okay, thus it prevents conduction of the of thermal energy from the drink to the outer side. So understood why, children, the surface, the glass bottle surface is made into a silver color or a silver surface or a shiny surface to avoid radiation. Why the vacuum? To avoid conduction. Yes, children, and the liquid inside stays hot for a longer period of time. Now look at this double glazed window which reduces thermal energy transfer into. So if there's too much of heat, it cannot pass through this. If it is too cold, if it is freezing cold, it's snowing outside and the inner area is heated, it does not allow the heat to move out due to this double glazed window. Okay, the picture shows a double glazed window. There are two layers of glass separated by a thin layer of argon gas. Argon is a poor conductor. Why? Because as we know, the outermost shell of argon is complete. It does not participate in any kind of action. It is inert. I will not. They don't have an electron to give out to conduct electricity. They do not want any electron to come into them and give heat to them. So argon is a poor conductor of heat. In the picture, you can also see insulation inside the wall. Yes, there is some kind of insulation. I guess this is what is the insulation, children. Okay, there is a space between the two layers of brick walls that is filled with foam. Yes, the foam is also a poor conductor as also fill the spaces to prevent convection currents from forming inside the wall. So the air particles get trapped into the foam. The foam has big holes in them. So if air particles come, they get trapped into them. Okay, and thus not giving out the heat. Alright, children, science can make life easier. Car windows can be covered with silver material to reflect radiation from the sun. So if there is sunlight coming inside the car and making the car hot, okay, what needs to be done? A silver material reflector should be put on the glass windows or the windshield to keep the radiations of the sun away, and the inside of the car does not become hot when you sit in it. This helps to stop the car becoming too hot when parked on a sunny day. That has brought us to the end of ways of transferring heat, which children remember in your examination. A lot of day to day application based questions will come. You will have to use your brains, rack your brains, cudgel your brains to think which method has been used to avoid or to transfer heat. Okay. Now, coming to cooling by evaporation. What exactly is evaporation? Evaporation takes place when the topmost layer of any liquid, okay, becomes active due to the atmospheric heat that it comes in contact with. So the topmost layer of the liquid becomes very active and moves and breaks the bonds of attraction and moves out into the air, giving a rise to the next layer coming in contact with the atmospheric layer or with the atmospheric air. Okay, so evaporation is the change of state from liquid to gas. In simple terms, think of a liquid such as water at room temperature. So evaporation takes place at room temperature. The particles in the water are moving around in random directions. Some of these particles move faster than the others, and the speed of the particle is also random, and the top layer particles of water or liquid are move the fastest as compared to the inner layer of inner water particles. The word random means unpredictable. The particles in the water that are moving faster have more energy. Some of these particles have enough energy to escape from the surface of the liquid and become particles of gas. Some of these are pulled back into the liquid, but others have sufficient energy to leave and not get pulled back. This is summarized in the diagram. So the lowest level of energy remains in the liquid. The medium energy particles can escape liquid but get pulled back, and the highest levels escape into the air. So when the particles escape into the air by evaporation, apparently it lowers the atmospheric temperature. It cools the surrounding air. Okay. Temperature is a measure of average energy of a particle. Think about water again. Remember that the particles in water have different energy. The topmost layer will have the highest amount of energy. When the particle with the highest energy escape from water, this will lower the average energy of the particles that remain. Therefore, the temperature of the water will decrease. The water will become cooler. So, evaporation causes a cooling effect not only in the water but also in the surrounding air. You can feel the effect of this when you get out of a swimming pool. When the water on your skin evaporates, the particle with the highest energy escape, causing the water to cool, and you feel cold when you walk out or come out of the swimming pool. The thermal energy in the water droplets on your skin comes from the thermal energy in the water comes from your skin. Correct. Therefore, the energy provided to change the state of water from liquid to gas comes from your skin. Okay, as your skin loses thermal energy, this causes the cooling effect. Yes, have you ever seen any shopkeeper, any small shop or storekeeper? He very often in the afternoons, okay, sprinkles water in front of his shop, simply because the floor or the ground becomes really hot, emitting a lot of, or giving out a lot of heat. Okay, so when they sprinkle water, the water particles, okay, get the or take the heat from the hot ground and they evaporate. They change their state from liquid to gas, thus cooling the temperature of the ground. As the ground has lost the thermal energy, okay, losing thermal energy means cooling down. So the surface of the ground cools down, lowering the temperature in the surrounding air. When we are too hot, our skin produces sweat. Why? Okay, many people think that the liquid of the skin alone causes the cooling. No, but since the sweat was produced in the skin, it is the skin which is providing the thermal energy to the liquid or the sweat. The sweat the sweat particles, okay, they get the thermal energy to drift away or to fly away. Okay, they've taken the thermal energy from the skin, children. So taking away thermal energy from the skin means cooling the skin, and the temperature of the skin comes down. It lowers the skin temperature. Some animals that do not sweat very much cover themselves in water to cool down. The evaporation of the water gives the cooling effect. Okay, in very humid conditions, sweat may not be able to evaporate. This can be dangerous. Okay, as body temperature increases without the cooling effect. Okay, okay, it can be dangerous if you do not sweat. Okay, and even if you sweat, okay, it does not evaporate. Okay, the body temperature will continue to rise, causing heat strokes. Okay, evaporation and cooling of other liquids. Different liquids have different forces holding the particles together. Okay, the point of evaporation of water is what? The other point of boiling point is 100 degrees, but is there a point of evaporation? Does water evaporate at any specific temperature? No, it can happen at room temperature. Now the room temperature can be 24 degrees, 26 degrees, 30 degrees, you may not know. Okay, so there is no specific evaporation point. But however, different liquids have different forces holding the particles together. Some liquids have forces between particles that are weaker than those in water, and some are stronger than water. Yes, some liquids, such as perfumes, have weaker forces, and so they evaporate easily. Okay, perfumes are designed to evaporate quickly and easily so that you start smelling good. Okay, if you put equal volumes of perfume and water in the same temperature on your skin, the perfume will feel cooler. Okay, because it takes the thermal energy from your skin. Okay, perfume evaporates faster than water, so removing the thermal energy faster from your skin, giving your skin a cooling effect. Other liquids, such as liquid soap, which are comparatively dense, okay, have stronger forces between the particles. See, a liquid soap, it is quite thick as compared to the perfume or water. Liquid soap evaporates much slowly than water. If you put equal volumes of liquid soap and water at the same temperature on your skin, the water will feel colder. Yes, water evaporates faster than liquid soap, so removes the thermal energy faster. Whatever I'm underlining, children, these are key technical terms that a teacher wants to see when you're writing your answers. There's a safety note: do not put any liquid on your skin apart from water, soap, or perfume. Okay, soap should be washed off from the skin with using plenty of water, otherwise, it may cause irritation. You'll keep scratching and scratching, and then you may have rashes. Other liquids, you never know if that liquid, the effect of that liquid on our skin is unknown to you. Do not do it. It may cause some kind of allergy. Okay, that was all for this chapter, children. Hope you've understood a lot. Thank you, and God bless you all.